Assalamu alaikum. This is Group A1 G1 presenting for EEE 206 Lab Project. The title of our project is Design of a Regulation and Feedback Control System for a Synchronous Generator with Simulink. Our group members are roll 1 to 6. The idea is to use Simulink built-in models to regulate steady-state operation of a synchronous generator which is connected to a time variable load. Here, regulation implies to monitor parameters and use them in feedback systems to control the governor set points and other operating parameters of the synchronous generator up to desirable limits within normal rating values. We will model the time variable load as a typical power consumption system, which has a characteristic load profile with time. As demands of power consumption changes over the course of a day, the generator must be capable of regulating its operating parameters in response to those changes. Otherwise, this can destabilize the particular power system. The variables we will monitor with sensors are terminal voltage, line frequency, and power factor. The whole point of this regulation system is to keep these variables within normal operating conditions even if time variable load forces them to alter. Here is the diagram of our Simulink model. Now my teammates will proceed to explain the functions of various components.
Because of the inherent group characteristics of a synchronous generator, the line frequency gets affected as we vary the active load. So to maintain a stable output frequency, we have to control the governor set points, which in turn will make the prime mover to rotate at the desired speed. We have implemented this basic idea using feedback control inside this frequency controller subsystem. Inside this subsystem, the model structure is consisted of two separate blocks. The first one is governor setpoint control and the second is turbine model. Inside the governor setpoint model, we have constructed a basic discrete PD controller. The PD controller takes two inputs. The first one is reference speed, which we want to attain, and the second one is current operating speed. The error signal gets passed into the PID controller box, which automatically calculates necessary governor setpoint value to reduce the error signal. We have used Simulink auto tuner to tune the PID controller with appropriate parameters. In the bottom portion, the error signal propagate after getting scaled by a group factor and added with the governor setpoint value. The next block just models a physical turbine by fast order transfer function, and later the turbine output is scaled by base torque value, which at last enters into the next section, which is our synchronous generator.
To control the terminal voltage, we have designed an excitation system where the main components are regulator, exciter, and a system stabilizer. Here, the terminal voltage is sensed and reduced to a DC quantity by a transducer, which is modeled by a time constant here. Output VC and reference voltage are the main inputs in this excitation system. At this point, VC is subtracted from the reference voltage to produce an error signal. Our main purpose is to reduce this error so that the terminal voltage can hold a stable value near this reference voltage. The error is amplified and the amplifier is represented by its gain K and time delay T. Regulator output is used to control the field voltage by a time constant T. A feedback block with gain Kf and time constant Tf is used to stabilize the system and damp out the oscillations. Finally, through a synchronous machine field circuit, we get Fd plus and Fd minus, which are the input field voltages in our synchronous generator.
Here we have three-phase varying load. This is a combination of 7 types of load. Now if we double click on the load, we can choose rated voltage, rated frequency, via ratings of the loads. We can also choose which type of load we want to work on. Now we will go to the sub-circuit. Here we can see these 7 types of load. There are unity increasing load, increasing leading, increasing lagging, lead to lag, lag to lead, varying, and overload. All of these switch loads are connected with a switch. Now, by clicking on the chosen load, the switch will be connected. Now, this whole circuit is modeled by using switches. It has been done by using step signals. For each switch, the time when the switch will be on is given.
We have included power factor correction in this subsystem. For this, we have added a simple math function so that if power factor is more lagging than 0.9, then a capacitor bank is automatically connected. If for any reason the generator's power exceeds the rated power, the circuit breaker disconnects it from the system. This is the circuit configuration of the circuit breaker. There is also always an initial load connected to the generator irrespective of the system.
The function of the dashboard is to demonstrate the simulation results. Here there are some plots and gauges to display the per unit values of our simulation results like terminal voltage, line frequency, power factor angle. There is also an overload indicator which activates when the load power is more than the rated power the generator can provide. Also there is a toggle switch to disconnect the generator in overloading condition at any time. So let's connect the leading to lagging load and simulate. From the results we can see the real power is almost constant but the reactive power is changing. The power factor is also changing from leading to lagging, and as it becomes more lagging the capacitor bank is activated to correct the power factor, and so the power factor is kept near 1. Let's run another load. So we can see the results from the dashboard. The real power is changing, also the reactive power is changing, so the power factor is changing, and our generator excitation system is trying its best to keep up with the load changes and keeping the terminal voltage as 1 per unit and also the line frequency constant. Let's try to overload the generator. So we can see the graph in real time. Now the generator is loaded with the load less than the rated load. But as the generator is overloaded, the power overload indicator is activated and we can disconnect the generator from the load with the circuit breaker, and then the load drops to 0. And then power delivered to the system drops to 0. Here we can also see the capability curve of the generator. This is for the simulation of overload. So this yellow region is the overloading region and this region is the normal region. That's our project and its simulations. Thank you.